Okay, so a few bits and pieces to show you before I start. In a random order, here's a chunk of basalt. And on top of it, I don't know if that shows up, it's reddened. It's where basalt's been heavily altered and having been exposed to a lot of humid climate. And I'll come back to that later in the talk tonight. Here's a piece of slate. Thin slate forms slabs, and you can see this green band running across it. It's a bed of sandstone that was originally in mudstone. And the slate splits quite independently of that original layering. More about that later. What else have I got to show you before I start? Oh yes, I mentioned last time that basalt was magnetic. Here's a compass, and here's actually a piece of dolerite. And if I hold it near the compass, I hope you can see the needle swing. Yep. So the magnetite that I mentioned last week in dolerite and basalt makes the rock magnetic. And then we're going to be talking about schist again. I'll just show you a piece of schist shining in the light. It splits into flat pieces. And this one here, green peridotite from the Earth's mantle that came up in a lump of basalt. Came up in basalt as a lump, I should say. And finally, this rock, serpentinite. This is what peridotite changes to when water is added to it. So I'll move on to the slides now and get started. Okay, so this is the fourth and final lecture on metamorphic rocks. And here are the questions I'm going to be addressing this evening, 6 of them. How and when were baked rocks used? The next one is how and when were other metamorphic rocks used? Thirdly, how are rocks recycled in nature? Fourth, how does the earth work inside? 5, was Ireland always at around 53 degrees north? And 6th, how was the earth created? You'll see that there's going to be a little bit more geology and less archaeology tonight, but I think it'll all come together. So here are the 6 rocks that I introduced you to at the beginning, 6 common kinds of rock from Ireland. And then the last one, bottom right, there is schist. And metamorphic rocks, schist is a metamorphic rock. They are simply sedimentary rocks or igneous rocks that have changed in appearance as a result of processes beneath the surface. So schist started out as mudstone. There it is, it glistens and it splits into wavy pieces. And all 5 of these can become metamorphic rocks. So how and when were baked rocks used? By baked rocks, I mean rocks that were heated by the close proximity of an igneous intrusion. And the biggest intrusions in Ireland are the 4 granites I mentioned last time, Donegal, Galway, Newry and Leinster. And here in the Leinster granite at Glendalough, which many of you will know, that's where the schist came from. And it was formed by heat from the granite. Here we are standing more or less on the granite, looking eastwards at the schist next to it in the margin, looking down the valley there. And this is what happened. In the zone marked with dashes there, arrowed blue, the hot granite baked the adjacent mudstone, and it also squeezed it as the magma forced its way in. And this turns the mudstone into schist. And it's the squeezing that's important here, as well as the heat, because the squeezing caused the little mica flakes that grew in the schist to line up with each other. Here is the little monastery in Glendalough, and here at Trinity Church, you can see the way the local rocks have been used. The schist has been used as the main building material, but around the arch there's lovely dressed granite that was used to support the arch. So let's leave Glendalough and look at some other baked rocks. And believe it or not, we find some at Knowth. This is the Neolithic tomb. And there in front of the entrance, lying amongst lots of quartz, white vein quartz that I mentioned earlier, are cobbles. Here's a cobble of granite, and here's one of a rock called hornfels. And this is made by the metamorphism of banded mudstone. So here we are, again, looking at the map of Ireland, and these cobbles that I've just shown you, the granite and the rock called hornfels, are believed to come from a beach at a place called Rathcore. And the granite is thought to be from the Newry granite, which has been brought by the ice to the coast. And where the granite came across adjacent, where the granite heated the adjacent Silurian mudstones, was baked and was turned into that rock called hornfels. So here's the cobble strand at Rathcore. Thanks to George Sevastopoulos for these slides and this bit of the story. And here close up, you can see a couple of those cobbles there in blue, the baked hornfels, baked Silurian mudstone. So what's the difference? They both start from mudstone, the schist we just saw, and now the hornfels. The schist is a result of heating and squeezing together, but if we get heat only, the grains grow rather randomly and make a tough rock called hornfels. The next rock formed by baking is this, porcelainite. This is a hoard of porcelainite axes, prized premium polished axe heads. And they really were prized and premium because they took a wonderful polish. And the polish was important because if the axe surface had defects on it, those defects could be the starting point for a stress fracture and the axe would break. But a beautiful polish means that the fracture doesn't get started to propagate and the axe will last for many years of use. These were so prized that they account for about half of the 20,000 stone axes that have been found in Ireland. And they were produced in two places in County Antrim, Rathlin Island and Teve Bullia. Let's have a look at those places. Here's Teve Bullia on the hillside. And here is, well, we mentioned Rathlin Island earlier because it's the home of the Bronze Age skeleton with the Amnion DNA about 4,000 years ago. So maybe this chap in his day was employed as an axe polisher, who knows? Well, just looking at this map, you can see the distribution of axe heads made of porcelainite from Teve Bullia and Rathlin. They've found in Scotland and England and Wales and all over Ireland. Enormous amount of trade. And I think that's one of the fascinating things about the Neolithic, the extent to which communication and trade took place. So how did this selenite form? Well, here we are back at the Giant's Causeway looking east, and you can see in the cliff there this red material halfway up the cliff, basalt above, basalt below. This red material, here it is in close-up, and this was formed because there was a long interval when the first lot of basalt came up before the next came down on top of it. And during that interval, the basalt got very intensely weathered. It got rotted and everything got dissolved away pretty well, except for iron and aluminium oxides and hydroxides. And the red color is from hematite. Well, it's this rock that was captured. It fell into a dike. Let's just go back to this slide here. Imagine a big dike cutting through, a big dolerite dike cutting right through that lot, and a block of that laterite, as it's called, this red material, a block of that laterite fell into the dolerite, completely enclosed by magma at 1100 degrees, and it got nearly melted to make this hard porcelainite. And this paper, recent paper, an interesting one, analyzed the porcelainite from the two locations and showed that about equal numbers of stone axes came from Rathlin and from Teve Bullia. And this paper also interested me because there on the first page in the introduction are this name, Agrell and Langley, 1958. And Stuart Agrell, here he is, he taught me. He was a wonderful mentor and teacher. And he worked on the Teef Bullia rock as an exercise. And it was an awful looking rock because the grains are so tiny in this hornfels. He was into lots of things, including he was one of the first PIs on the Apollo 11 mission. And here he is returning with his haul. That's him in the middle. And this was a photograph from the Daily Mirror, front page. And the caption was, "Guess what's in my bag?" And he was carrying Apollo 11 samples back from Houston. Okay, enough of Stuart Agrell. Let's move on to the other kinds of metamorphic rock. We've looked at the baked ones. What about the other kinds? Well, one of them is slate. And as I showed you at the very beginning, slate splits along cleavage to make slabs, which can be used for building or it can be used for roofing. So how is slate formed? Well, it's formed by sideways. Now, here is rock that has suffered sideways pressure. These are beds not of mudstone, or they're of limestone and shale at Loch Shinny in County Louth, and they've been buckled into folds by lateral compression. Now, if mudstone on its own is squeezed like this, folds are formed, as this cartoon shows. So these lines follow the bedding, and the folds are formed, and a slaty cleavage develops at right angles to the direction of compression. And here is that same piece of slate turned around to be in line with that previous drawing. The slaty cleavage is vertical, and you can see this green band, which is a bed of fine sandstone within the mudstone, completely independent of the slaty cleavage. The slaty cleavage has been superimposed afterwards. So mudstone then, we've seen that it can be turned into schist by heating and squeezing. By heat only, we get hornfels. And in this case, we've got very little heat. There's a bit of heat, but it's mainly squeezing has caused the mudstone to turn into slate. So the same starting material can end up here as 3 different products depending on the conditions of metamorphism. Right, now I'm going to turn to a very different metamorphic rock, 4 examples of which have been found in Ireland that I know of that are in the National Museum. Here's 2 of them. They are polished jade. Technically the name is jadeite, a rock made of jadeite, but commonly referred to as jade. These beautiful polished green axe heads, one from County Donegal and one from County Westmeath, but they were made in the Western Italian Alps. That's where they were found, and that's where they were made, down here. And in that region, large numbers of these jade axe heads are known, but they've traveled far and wide across Europe. I suspect that they were more for ceremonial use or kept as treasure rather than for everyday work because they are so beautiful. Now, the interesting thing about jade is that the metamorphism is incredibly high pressure. Here's, sorry, just to remind you of where they're from. This is the Western Alps near the French-Italian border. But this is what I was about to tell you. This is a diagram showing depth on this axis, 20, 40, 60 kilometers down below the surface, and temperature. And sodium feldspar, if it's squashed under enormous pressure corresponding to these kind of depths, it changes into a new mineral called jadeite and some quartz. And this is what the jade axes are made of. They were formed in conditions above this line. Here, the temperature 20, 200, 400, 600, 800 degrees. And the conditions were somewhere probably within that green ellipse, that sort of region. Now look where we are, 50 kilometers below the surface. Wow. So how did it get there and how did it get back? Well, this is the sort of model that we envisage. Shortening of the continental crust. The continental crust is buoyant and it sits inside on top of dense mantle. So when the whole lot gets compressed, the continental crust can thicken up, stick up as mountains and stick down as a kind of root zone like that. And this crust, if you remember from last week, from the surface to the moho is about 30 kilometers. So here we are, this would probably be about 90 kilometers if it's to scale, and 50 or 60 kilometers would be down here. So somehow all this lot has to be removed to get the jadeite to the surface. And that's perfectly possible because the crust sits, as it were, floating in the mantle, and it can be imagined to be like this analogue here of wooden blocks floating in water. The deeper down they stick into the water, the higher up the top floats above the water surface. So this is like the crust floating in the mantle. And this cartoon shows, same as I showed you earlier, but now colored, compression shown by the right arrows, thickened continental crust, and all the area that's been shaded there, has been the diagonal lines across it, is to be eroded away, leaving just 30 kilometers. If you wear off the top of the mountain will rise a bit more, and it'll rise up not as high as it was before, but it'll keep rising until there's only 30 kilometers left. So rocks deep down in the root zone of the mountain will end up at the surface. So that's how we think the jadeite got here. Well, back in Ireland now, there was a huge mountain range during the Ordovician period, about 470 million years ago. And it's represented by the rocks we find in Connemara, North Mayo, and Donegal in that sort of a horrible yellowy orange color there. So these are Precambrian rocks, sedimentary rocks and igneous rocks, metamorphosed in the roots of an Ordovician mountain range. And that mountain range is now completely eroded away. So we're looking at what was once the root zone of that mountain range. And these are the starting materials, again, sandstone, mudstone, limestone, basalt, and granite. And I just want to go through the kinds of metamorphic rocks, examples of what they can be changed into, with some archaeological examples thrown in for good measure. So let's start with quartz-rich sandstone. That changes into quartzite. And these are not from Ireland, from central Poland, but these are artifacts that have been shipped from quartzite. So here's mudstone. That changes into schist, as you know. That happens in the roots of mountains, as well as we've seen at Glendalough, where there's squeezing and heat together. But interestingly, sometimes the schist is like this. This is schist that got very hot and it partly melted. And the liquid that was produced was granitic magma. And it's filled here, it's filled veins that have later become a bit crumpled. Now, the schist contains some quartz and some feldspar. Those are the main ingredients of granite. So it's possible, if the schist gets hot enough, that those ingredients can combine and produce granitic melt. And that's exactly what happens if the temperature is high enough. Marble. Well, marble artifacts are well known in the Greek and Roman world and way beyond. Not so much in Ireland, but these ones from the Parthenon in Athens, it's worth bearing in mind that they're about 2,500 years old. So they were carved just at the beginning of the Iron Age. They're really very, very old. I believe the Greeks want them back. Okay, basalt next. Basalt changes into a number of things. So we call them all metabasalt, metamorphosed basalt. And here is an example of an axe head that's made from basalt, a metabasalt axe head. It's been wetted on the right to make it show up a bit. So that's one of the uses of metabasalt. And finally, granite. Granite can be metamorphosed and be turned into this rock called gneiss. It's one of the things that granite can be made into when it's metamorphosed. And on that last topic, that we go back to Ireland, up here, the island of Innistrahull off the Malin Head. And Innistrahull is made of gneiss that's been made from granite. It's the oldest rock in Ireland. I thought you'd be interested to know that. There's a photograph of ice made from granite, and that this granite was intruded 1,779 million years ago with an error of 3 million years, so I'm told. So these are the oldest rocks in Ireland then. Okay, so there we are. There's quartzite, schist, sometimes melted schist, marble, metabasalt, and gneiss. But there's a space here on the right because there's another rock that I haven't mentioned that can be turned into metamorphic rock, and that's this, peridotite, the mantle peridotite that comes up in basalt. If that becomes metamorphosed, it can be converted into two kinds of rock. One's called serpentinite, and the other one is called soapstone. Let's have a quick look. Here's a soapstone lamp. Soapstone is very, very soft. It's very easy to carve. Here's a soapstone lamp from northern Greenland, but it's Bronze Age. Here are two soapstone molds that carved for casting bronze. They were found in northern Norway. Here's a map of Denmark. All those triangles are where soapstone artifacts have been found. So they really are common. I suspect there are some in Ireland, but I'm not familiar with them. And then serpentinite. It's another thing that the peridotite can be turned into. Here's some objects from Switzerland. They look like roughed out axes and other objects, again from the late Neolithic. Now, just to show what's going on, peridotite is a rock that has no water in it at all, and it reacts with water to make these two kinds of rock. Peridotite plus water can be turned into soapstone, and peridotite plus water can be turned into serpentinite. So it's not, in this case, it's not just heat and squeezing, but it's the addition of water to the rock that leads to metamorphism. Okay, then, let's leave rocks behind for a minute and, well, not leave them behind, but let look at them from a different angle and to ask the question of how rocks are recycled in nature. And going back to the first lecture, I told you that sandstone was formed by a succession of steps. Number one was erosion, transport number two, deposition on the seabed, and then burial, which is number four, to convert, to produce sandstone. But the story doesn't end there because, of course, the deeply buried rocks have to be brought back to the surface for us to see them, as seen in this sea stack. Well, we can summarize that sequence of events in a little diagram like this, little loop: weathering and erosion, transport, accumulation, burial, heating and lithification, making sandstone the sedimentary rock. And all sedimentary rocks form like that. And then uplift brings it back to the surface where weathering and erosion can start all over again and so it can go round and round. Well, now that we know about metamorphic rocks, we can extend this loop to add another circuit where sedimentary rocks get deeply buried and intensely heated, mostly in mountain root zones, to make metamorphic rocks. And those metamorphic rocks can be uplifted, brought back to the surface where they can be weathered and eroded and rejoin the cycle. So we can go one further, because if metamorphic rocks get very intensely heated, like we saw in that schist where granite had started to develop, we can add this loop. This is partial melting of schist. The granite sweats out of it. Granite can collect, and when there's enough of it collected, it can rise buoyantly up through the crust and end up either as intrusions, plutonic igneous rocks, or it can actually come up to the surface as volcanic igneous rock. And these rocks can also enter the cycle and become weathered, eroded, and transported and brought round. Now, of course, these igneous rocks, they don't have to be transported and accumulated as sediment to end up as metamorphic rocks. So we can add two more lines, dashed lines there, bringing them across to metamorphose them, so we can get metamorphosed igneous rocks. So the circuit's getting a little bit busy now, but it's still fathomable. Let's go one more step and say, well, we haven't seen anything of basalt. And that's where we take in basalt, which comes as magma from the mantle by decompression melting, and it can join the cycle as fresh new material, either as plutonic rocks under the ground or as basalt erupting onto the surface and become weathered and eroded and become part of the cycle. And also, of course, when mountains are developed, that intense compression and deformation that goes on in the root zones can lead to pieces of the mantle from below the moho being incorporated into the roots, and that brings us the peridotite, which can become metamorphosed to make serpentinite and soapstone. So there we are, a really quite an elaborate system of loops and cycles that link rocks together. And this whole diagram, if you like to see crust and mantle, I've colored it up here. Just it's the same diagram, but just so let's move on to the next question, which is, how does the Earth work inside? Here's a diagram showing the crust and the mantle. And I've shown you some of this before. This is the continental crust, which is about 30 kilometers thick there. And here is a mountain range where it's been thickened up by compression. But here, it's very thin, and this is oceanic crust. It's only between 5 and 10 kilometers thick, much thinner than the 30 kilometers or so in the continental crust. And going to that same little model I showed you before of floating wood blocks, okay, here you can imagine the continental crust, which is less dense than the mantle, floating like those blocks. And where it's very thin, the surface is at the lowest point of all, so low, in fact, that the ocean water floods in and covers it over. Okay, so I also told you last time about going down through the crust into the mantle. We go through this boundary called the moho, where the speed of sound, the seismic speed, goes up from 6.5 kilometers per second to about 8 kilometers per second, a sudden jump. That defines where the crust stops and the mantle starts. And the mantle goes all the way down, nearly 3,000 kilometers to the core. But there's a very important distinction to be made within the mantle as to how strong it is. The topmost 100 kilometers of the Earth is a strong, rigid outer layer. It's called the lithosphere. So with 30 kilometers of crust, another 70 will make us that 100 of strong mantle. The strong mantle goes down, it grades into weak mantle as the temperature goes up. And this hot mantle, this is the mantle that behaves, as I mentioned last week, behaves like pitch and is capable of flowing, albeit very, very slowly. It's still solid, but behaves slowly. There's the man with his pitch about to drop out of the bottom of the beaker, out of the bottom of the funnel. So, change the diagram slightly, because what I put on top here is oceanic crust. I've suggested it's 5 kilometers thick, but we still need 100 kilometers of this outer layer called the lithosphere. And the lithosphere is about 100 kilometers thick, regardless of whether the crust is continental or oceanic. So if we have only 5 kilometers of oceanic crust, we'd have something like 95 kilometers to make up the 100 of strong mantle. So this strong outer layer is very important in understanding how the Earth works inside. And 3 things about it. First of all, this outer layer is dissected by deep fractures that go right down through the whole 100 kilometers and divide the lithosphere into separate segments called lithospheric plates, or just plates. And these plates are curved, cover the Earth's surface, and they move independently of each other. And where they are in contact, where they touch, that's where earthquakes occur. So here's a map of the world showing earthquake epicenters. You can see lots and lots of them around the Pacific there, but if you look carefully, you can see a line of them all the way down the center of the Atlantic over here to the right. And you can see more lines within the ocean. These earthquakes mark the edges of plates. So I've joined the dots here with a red line, and that defines these segments of the lithosphere called plates. And there's 8 big ones that I've numbered there. These have got names. I won't go through all the names, but this one, number 5 in the middle there, is where is known as the Pacific plate, because it fills up most of the Pacific Ocean. Number 2 over here is the African plate. Number 3 below is the Antarctic plate, and so on. So there are 8 major plates and a number of much smaller ones that haven't been named. That is the Arabian plate. It's a small one. So 8 major plates with deep fractures going right through the lithosphere down to the weak mantle below. And these move relative to each other. So there are 2 situations that I'm going to address where they move apart from each other and where they converge. So let's take a situation where they move apart, as for example is happening down the middle of the Atlantic Ocean. This cartoon, before I get going, is a summary of what I've just told you. About 100 kilometers, the outer 100 kilometers of the Earth is called the lithosphere. And it's a combination of strong mantle with whatever crust is on top of it, either continental crust or thin oceanic crust. The combination makes this 100 kilometers of lithosphere. And below the lithosphere then is weak mantle. And the lithosphere is divided up by these deep fractures into separate plates. Right, let's look then at what happens when the plates are moving apart. So here we are, plates moving apart. What happens? The diverging plates lead to the creation of new oceanic crust. It's about 5 kilometers thick, and it's made entirely of basalt, dolerite, and gabbro, the fine, medium, and coarse-grained products of when basalt magma freezes. And I mentioned this formation of basalt last week in the context of this diagram: decompression melting. Hot, weak mantle from beneath the lithosphere rises to fill this widening gap. And as it rises, loses pressure, it crosses over that sloping line where melting begins. It forms roughly 25% liquid basalt and 75% leftover peridotite, separates out, and the liquid comes to the top to form the oceanic crust. And cools down, and it makes more lithosphere, adding to what's already there as the crack continues to be fed by more weak mantle from below. And here is a picture showing the Atlantic Ocean with the age of the basalt in the ocean floor. The red is the youngest, and that's down the middle where the crack is still opening up. And then symmetrically on either side, we've got older crust in green, that's between 50 and 100 million years old, and blue is more than 120 million years out near the edges when the crack first started opening up. And an interesting thing goes on at the central part, the mid-ocean ridge as it's called. From place to place along that ridge, we find these amazing features called black smokers. What's happening is hot fluid at several hundred degrees centigrade is pouring out of these little vents. And that's produced in this way. Here's the hot magma. Seawater makes its way down cracks through the basalt and gabbro that forms the new crust, even down as far as the peridotite. It's heated up, gets lower density and it comes pouring out through the black smokers as hot fluid. And as this fluid goes through the basalt and gabbro peridotite, it metamorphoses those rocks. And the peridotite, for example, takes up lots of water to be converted into serpentinite and soapstone. Right. Let's move to a different situation. This is where a plate with oceanic crust is descending under another plate with continental crust on top. And what happens here is that the descending plate gets hotter as it goes down, and it gets to the point represented by this yellow circle where the water is baked out of the serpentinite, and the hot water, the steam, if you like, that's released, it triggers melting, it triggers decompression melting down here, and the mantle here starts to rise up and eventually comes out as volcanoes at the top. But this magma is now full, charged with water. And as I mentioned last week, magma that's charged with water erupts in an explosive way because that steam suddenly escapes once the pressure comes off near the surface. So above the place where the plate is descending, then we have chains of volcanoes, and chains of volcanoes are particularly well known all around the Pacific Ocean where this process is going on, called the Ring of Fire. And we get magnificent explosive volcanoes like Pinatubo, which erupted in 1991. That leaves one last situation. That's where the two opposing plates both carry an outer crust, which is continental crust. Now, this is messy. And I've written here, when a plate with continental crust meets a similar plate head on, the crust on the descending slab, that's on this side, because it's buoyant, it becomes detached from the mantle below. And the combined continental crust from both sides gets very thick and deformed and creates a buoyant mountain range. And the metamorphic belt that I mentioned in the west of Ireland from the Ordovician would have been formed in this kind of way, as are the Alps and the Himalayas today. There's a nice picture of the Alps, formed because of the buoyancy of crunched up continental crust where two plates are converging. Okay, so that's a summary of how the Earth works inside. That whole process that I've gone over is called plate tectonics. I'm sure you knew that, but there we are, plate tectonics. That brings us to question 5. Was Ireland always at around 53 degrees north? Well, for a long time, Ireland was part of a supercontinent. This is called Pangaea, shaped like a letter C. All the continents joined together, and this situation lasted from about 335 to 175 million years ago, between the middle of the Carboniferous and the Jurassic time. Huge continent. But this huge continent called Pangaea no longer exists. It's cracked open. It's cracked open, and the continents have moved apart to form the separate continents that we know today. So this is Pangaea. Let's have a look to see how Pangaea evolved into what we see today. During the Ordovician period, something is interesting with regard to Ireland, and that is that the north and northwestern half of Ireland up here was separated from the southeastern part by a huge ocean, a bit like the Atlantic. And the red dots signify the positions, as it were, of volcanoes, like the volcanoes around the Pacific. And the grey wacky sandstone was deposited on the floor of this ocean. I mentioned that happened during the Silurian period, produced the greywacke that was found at Clocker Head to make the curbstones at Newgrange. Anyway, the two sides came together and they'd met by the end of the Silurian period. And at this time, Ireland was south of the equator, and it moved steadily northwards after that. So going through geological time, here in the middle are the geological periods from bottom up: Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, and Cretaceous, and then the Tertiary and Quaternary at the top. So it's a very concise summary, but in the Silurian, Cambrian, Ordovician, and Silurian, that's the lower Paleozoic, this Iapetus ocean existed. And the continents on opposite sides converged and met by the end of the Silurian period. And then what was Ireland moved northwards. And during the Devonian period, red sandstones were the order of the day. And these correspond, if you like, to the southern desert latitudes. The northward movement continued, and during the Carboniferous, Ireland was around the tropics. And we get tropical seas with that lovely Carboniferous limestone that I've mentioned a few times. But the northward migration continued, and during the Permian and Triassic, we were back in the latitude of deserts, and the new red sandstone was what was deposited. And by this time, Pangaea was well put together, and from the Jurassic onward, Pangaea broke up. Okay, well, that brings us to the last of the 6 questions. Biggest question of all: how was the Earth created? And I haven't forgotten that archaeology is part of this story. So here is a very interesting archaeological artifact. It was found in Tutankhamun's tomb. He died around 1324 BC. And this is a dagger with a gold handle and a gold sheath, but the blade is made of iron. Now, this was 800 years before the Iron Age began. So what is going on? Well, the answer is, and some of you I'm sure know this, that the iron came from an iron meteorite. And it's meteorites that give us the answers to the questions about how the Earth was formed. So here's the time scale. The Earth was formed here in the middle, 4, 5, 6, 7 million years ago. The solar system began. That was well on in terms of actual time, which began 13,700 million years ago with the Big Bang. Here we are today, and the oldest rocks in Ireland are only about here. So there's a lot of time going back before the very oldest rocks in Ireland. So what went on 4, 5, 6, 7 million years ago? Well, one of the clues is in this view, this is an artist's impression of the Milky Way galaxy in the background and the planets, greatly enlarged, orbiting the sun, and they're all in the same plane going in the same direction. And that suggested many years ago that the whole lot began as a big rotating disk of dust and gas around the young sun, like this artist's impression here. And within this of gas and dust around the newborn sun, the planets are growing. There's a few shown here, small planets, baby planets growing out of the gas and dust. But those baby planets merged and grew bigger and eventually ended up as the planets we know today. But between the orbits of Mars and Jupiter, something didn't go to plan. We don't get a big planet there. Instead, we get lots of asteroids. Asteroids are broken bits of many baby planets that never managed to merge into a big planet at the beginning of the solar system. Here we are, Sun in the middle, Mercury, Venus, Earth and Mars. Jupiter is off scale. And these are the asteroids, leftover bits and pieces from that early stage of the disk going around the young sun, where small planets were formed, but they never merged into a big one. And here's one of the bigger asteroids, Vesta, it's a baby planet about 500 kilometers across. Now, these asteroids have collided with each other from time to time to make many fragments, broken asteroids, and some fragments reach Earth as meteorites, as in this case of the Chelyabinsk meteorite in 2013. Well, when a meteorite is examined, here's a saw cut through one of the Irish meteorites, the Dundrum meteorite. It's a so-called chondritic meteorite. And the sawn surface shows that inside it's made of bits. It's a kind of cosmic sandstone. And about 10%, 10 to 15% of the bits are shiny there. They're little flecks of metal, iron. And the rest, the brown, is made up of spherules of peridotite called chondrules. This kind of meteorite, chondritic meteorite, is very common. About 86% of all the meteorites that land are chondritic meteorites. This is what chondrules look like under sky electron microscope. This big one here is about 1 millimeter across, little spherules of peridotite that was actually molten and partly crystallized. But not all meteorites are made of chondritic material. Like Tutankhamun's dagger, some are made of iron. About 6% of the meteorites that land on Earth are made of iron. And this is a sawn surface. There's a wonderful pattern inside, but I won't go into the pattern. It's a piece of iron. So where did this come from? And the answer is that these small planets, these small chondritic baby planets, some of them got hot and melted. And the molten iron drained down to form a molten iron core, which eventually solidified into iron metal, and it left behind a peridotite mantle. So some of the baby planets did this. And it seems that the whole Earth, our whole planet Earth, did something the same. It started off as chondritic material, it got hot and separated to form an iron core and a peridotite mantle. Now, there's some good evidence to support this idea. It's the chemistry of chondritic meteorites. It matches the chemistry of the sun. This diagram shows on the vertical axis the chemistry, the amount of each element in the sun. And I've picked out some elements here, abundant elements like iron and magnesium and silicon at the top here, rare elements like scandium, strontium, and zirconium down here. And each number here, this is a log scale, each number is 10 times more abundant than the number below it. So there's huge amounts of iron and magnesium and silicon and really relatively little of these elements down here. And the same on this horizontal axis, this is the amount of each element in chondritic meteorite. And you can see there's a lovely one-to-one relationship. The sun and the chondritic meteorites have got these elements in exactly the same relative proportions. And this confirms what we might have expected if everything started from a disk going around the new formed sun. It all started with material of this composition. This is the primordial composition from which the whole solar system was made, and hence from which the Earth is made. And you might ask how we know the chemistry of the sun. Well, here's the spectrum of sunlight. Sunlight passed through a prism, and the spectrum's been stretched right out into a long strip and stacked in this way so you can see it all. And these tiny dark lines that you can see in different parts of the spectrum of colors, they correspond to chemical elements in the sun. And the darkness of the line corresponds to the amount of the element. The darker the line, the more of the element there is. So it's possible to work out the chemistry of the sun from this. Okay, so the last question is, where did the disk and the new sun come from? Well, here we are again looking at this picture of a galaxy like our own, a spiral-armed galaxy. And within the galaxy, there are 100,000 million stars, as I mentioned in the first lecture. But there are also other things. And one of those other things, not stars, are huge clouds of gas and dust, like this one here called the Orion Nebula. Huge cloud of gas and dust where new stars are actually forming today. What happens? This cloud of gas and dust becomes gravitationally unstable here and there, as this cartoon shows. So there's a huge cloud of gas and dust. This little patch here has become gravitationally unstable and has fallen in on itself. And most of the material has ended up going to the center to form a new star. But because of the angular momentum of that fragment of the cloud, the whole lot is spinning. So we end up with a new star and a spinning disk around it in this way. We've been able to image those disks around new stars using powerful telescopes like this one here, the ALMA telescope, the Atacama Large Millimeter Submillimeter Array in the Atacama Desert in Chile. And this is one of the beautiful images it's produced. A new star in the center, and here is the disk of gas and dust that's illuminating. And these dark rings in it are where it appears that planets have grown, have developed, and used up the dust so that there's nothing to illuminate. And I'll finish with a simulation of star formation, which is a mathematical model produced by this fellow Matthew Bate. This lasts for about 2 minutes, and that was a huge cloud of gas and dust, and it's collapsing under its own gravity, and it's gone into kind of strands, and material is going into lumps, and the first lumps are forming stars. Now we're going to zoom in and watch it again. Here we are, zooming in and watching this continued collapse of the gas and dust to form stars. And it's not just static, it's very far from static. The whole lot's dancing around. Those white dots are the newly formed stars as the material forms together. And each one of those dots would have a disk of gas and dust around it from which planets would form. Haven't finished yet. If you notice in the top right corner, it's the time in years. It's 250,000 years have just elapsed. So if this really is a good analog for the formation of those stars forming now, if this is a good analog for the formation of the solar system, rather interesting symmetry to think that the timescale for things at the very beginning, the formation of the new sun and its disk in 200,000 years or so, is really rather similar to the period of time at this end of the time spectrum when human beings have inhabited the planet. So with that, I'll end and thank you for listening.